My name is David Hawk, and this is my lab report on the simple pendulum. In this experiment, I investigated the factors that affect the period of a pendulum swing. I tested how the period changes with the angle of release and the length of the string, and compared my results to the theoretical model for simple harmonic motion. The goal of the lab was to verify the physical model for a simple pendulum. A simple pendulum is a mass suspended by a massless, stretchless string, and for small angles, its motion can be described as simple harmonic motion. The main physics principle I use is that the period t, the time for one full swing back and forth, is related to the length of the pendulum L and the acceleration due to gravity g by the equation t equals 2 pi times the square root of L over g. This means that the period should only depend on the length, not the mass of the small starting angle. The main result that I discovered was that my data strongly supported this model, showing a clear relationship between period and length, while the period was independent of the angle. The model for a simple pendulum comes from applying Newton's second law, F equals ma, to the swinging mass. The restoring force is a component of gravity. For small angles, this leads to simple harmonic motion. The key equation is, as I stated before, t equals 2 pi times square root L over g. This tells us two important things. First, the period t should be proportional to the square root of the length L. If you plot t versus the square root of L, you should get a straight line. Second, the slope of that line should be 2 pi over root g, which I can use to calculate the acceleration due to gravity. I assumed the string was massless and that the air resistance was negligible. I tested these principles by seeing if our data matched the predicted relationships. For our system, I had a mass attached to a string, suspended from a fixed hook. The surroundings included the air and me timing the swings. My initial conditions were the starting angle, which I calculated from the height the mass was pulled back, and the length of the string. The procedure was straightforward. For part 1, I kept the length constant and changed the string angle, and in part 2, I changed the length of the string, while I tried to keep a small, consistent angle. For each trial, I measured the time to 10 full periods to reduce timing error, and then divided by 10 to find the period for one swing. This method gave us the period data I needed to compare my models. Here are the graphs to summarize our findings. First, the period versus angle graph had a very low r-squared value and a nearly flat slope. This shows that, as the model predicted, the period is essentially independent of the starting angle for the range we tested. Next, the period versus square root length graph was a beautiful straight line with an r-squared value of 0.99. The slope of our line was 1.8847 seconds per square root meter. According to the model, the slope should equal 2 pi over root g. Using our slope, we can solve for g. Doing this calculation gives us a value for g that is very close to the accepted value of 9.8 meters per second squared, with a percent difference of only about 6%. Our results strongly support the theoretical model for a simple pendulum. The period was constant for different angles and showed a clear square root dependence on length. However, our measured value for g was a bit off. The major source of error was human reaction time in starting and stopping the timers. Each period had an uncertainty of plus or minus 0.02 seconds, which adds up over 10 periods. For the what if question, a key question is, what if we used a heavier mass? The model predicts the period does not depend on mass. I would expect that if we repeated the experiment with a heavier mass, the period would stay the same, because while the gravitational force increases with mass, the inertia also increases proportionally, canceling out the effect. For the what does it mean question, our model for the pendulum's motion depends on a net restoring force provided by gravity. But if we think about the forces on the mass while it's hanging straight down and at rest, the net force is zero. Is it possible to say how many pushes and pulls are being added to give that zero net force? In that case, we can actually identify the two main forces, the downward pull of gravity and the upward pull of tension in the string. These two forces are equal and opposite, adding together to give a net force of zero. This is a key assumption in our model, that the string tension always adjusts to balance the component of gravity along the string, leaving only the perpendicular component as the restoring force. In conclusion, we successfully verified the physical model for a simple pendulum. We found that the period depends on the square root of the length as independent of the mass and the starting angle for small angles. Our calculated value of g from the slope of our data was close to the accepted value. The small discrepancy can be explained by our measurement uncertainties. To improve the experiment, we could use video analysis to eliminate human timing error, providing frame-by-frame data for a more precise period measurement. Thank you for watching.